Hi there, and welcome back to the College Physics series. In today's lesson, we're going to be covering a fascinating type of motion that you see every single day, and that is circular motion. Think about a car driving through a curved path, or a roller coaster at the top of a loop, or even a satellite orbiting the Earth. What keeps these objects moving in a circle? By the end of this video, you'll be able to understand the key principles of circular motion. You're going to be able to calculate the centripetal acceleration of an object, as well as see how this acceleration changes when we vary speed and radius. Be sure to download the guided notes that are in the description so that way you can follow along with me. Thank you for being here. Now let's get started. To explore circular motion, let's first define it. Circular motion is any motion where an object travels along a circular path. Today, we'll focus on uniform circular motion, where an object's speed remains constant as it moves around a circle. But notice something interesting. Although the speed doesn't change, the direction does. This means the velocity is always changing, even in uniform circular motion. The guiding question we're going to focus on today is, how do you think this constant change in direction affects the object's overall motion? In circular motion, the velocity vector at any point is always tangent to the circular path. So in the case of this circle, if I drew a point right here, this is the point in the object's motion, and the object is going around the circle in this direction, then the velocity vector will be tangent, just a straight line that only touches the circle at one point. If the object were here, then the velocity would point tangent. If it were here, it would point tangent, which is straight down. And if it were here, it would just point straight towards the right, only touching the circular path at that one point. To maintain circular motion, the direction of the velocity must continuously change, which requires acceleration, even if the speed is constant. This acceleration is called centripetal acceleration. Centripetal acceleration just means that the acceleration is directed toward the center of the circle, almost like a magnet is pulling on it. This center-seeking acceleration keeps the object moving in the circle. So at any point along this path, the acceleration will always be pointing towards the center. The formula for centripetal acceleration is as follows. The formula is AC equals V squared over R. Let's break this down. AC stands for centripetal acceleration. V represents the speed of the object, and R represents the radius of the circular path. The centripetal acceleration increases if the speed increases or the radius decreases. This relationship gives us insight into why faster moving objects need more force to stay in a tight circular path. Think of a car taking a sharp turn quickly, and we will discuss this when we talk about centripetal force in a later video. For now, let's do some quick examples. So here I have the formula for centripetal acceleration. What happens if I double the speed? How does that affect our centripetal acceleration? Well, for me to double the speed, instead of V, I'm going to put 2V, because that's the velocity squared divided by R. I want to see how this affects the centripetal acceleration. Well, if I expand it, 2V squared becomes 4V squared over R. Notice this right here. This is V squared over R. That's just AC. So I get 4 times the centripetal acceleration. So by doubling the speed, I end up increasing the centripetal acceleration by a factor of 4. What happens if I double the radius? Here's the formula for centripetal acceleration. What happens if I double that radius? Well, I can still separate the V squared over R from that 2 in the denominator. And so what happens is that I bring out the 1/2 in the front, and the V squared over R just turns into AC. If I double the radius, then I end up multiplying the centripetal acceleration by a factor of 1/2. So basically, you cut it in half. These examples help to show you the relationship between the radius and the speed to the centripetal acceleration. Let's do a conceptual example. The conceptual example reads, an object is moving in uniform circular motion. What changes could you make to double its centripetal acceleration? So I'm going to start with our basic equation, V squared over R. I know that both the speed and the radius affect my centripetal acceleration. Let's first explore the speed. I want to figure out by what factor I need to multiply the speed by in order to result in double the centripetal acceleration. Now, this might look funny, but this x just represents some number. It's just some number that I'm multiplying the speed by. If I'm going to increase it, that number should be greater than 1. If I want to decrease the centripetal acceleration, I have to multiply the speed by a factor that is less than 1. So how I'm going to solve this is that I'm going to replace the AC for its equation so that it looks like this. So instead of AC, I'm going to replace it with v squared over r, and then I'm going to solve for x. On the left-hand side, I get to expand this xv to the power 2 as x squared times v squared over r times 2v squared over r. Sorry, this is an equal sign. So what I'll do first is I'll multiply r on both sides, because that's going to cause all the r's to cancel. I'll be left over with x squared times v squared equals 2v squared. If I divide by v squared on both sides, then they cancel out. Continuing my work over here, I get that x squared is equal to 2. If I want to figure out what the value x is, I need to take the square root on both sides. Turns out I have to multiply my speed by a factor of the square root of 2 in order to double my centripetal acceleration. So one way to double the centripetal acceleration is to increase speed by a factor of square root of 2. So if I multiply the speed by the square root of 2, I'm going to double my centripetal acceleration. I can repeat this process if I put the x by the radius. So double my centripetal acceleration is going to be equal to v squared over x times r. So now I'm affecting the radius. What I'll do now is I'm going to replace AC with its equation, v squared over r. That's going to be equal to v squared over x times r. To clean this up, I'm going to multiply by r on both sides so that it cancels on the right-hand side and cancels on the left-hand side. Next, I'm left over with 2v squared equals to v squared over x. Using a mathematical trick, I can swap the positions of the x and the 2v squared. So I'm going to get that x equals to v squared over 2v squared. I get my v squareds to cancel. X is equal to a half. So the second way that I can double my centripetal acceleration is to halve the radius. And those are the two ways in which I can double my centripetal acceleration. Let's try a very basic problem. This next example reads, imagine a car rounding a curve at a constant speed. The radius of the curve is 50 meters and the car is traveling at 20 meters per second. What is the car's centripetal acceleration? If we have a car that is rounding a curve, that indicates that it's following a circular path. So that's going to ring a bell in our heads. The next thing that solidifies uniform circular motion is that it's rounding this curve at a constant speed. So if you have a circular path at a constant speed, uniform circular motion should be screaming in your head. So if that did not give it away, when the question asks for centripetal acceleration, that also gives away that we are in a scenario that involves uniform circular motion. So this is our typical plug and chug type problem, where our centripetal acceleration is the speed squared divided by r. I know that the speed is 20 meters per second. Never forget to square the speed, and the radius is 50 meters. 20 times 20 is 400. Meters per second times meters per second is meters squared per second squared. And I'm dividing it by 50 meters. 400 divided by 50 is 8. And when I simplify these units, I'm going to get meters per second squared. That would be the centripetal acceleration of this car. Before I give you a try-it-yourself problem, let's evaluate what we've learned by going over the key ideas. The first key idea of this lesson is that an object moving in a circle at a constant speed still experiences continuous changes in velocity because its direction changes. The second key idea is about centripetal acceleration. This center-seeking acceleration allows an object to maintain a circular path and is given by AC equals v squared over r. The third key idea is constant speed but changing velocity. While the speed in uniform circular motion stays the same, the velocity is constantly changing due to the continuous change in direction. Here's a try-it-yourself problem for you. The try-it-yourself problem reads, if an object in uniform circular motion suddenly experiences triple the centripetal acceleration, what could have changed about its speed or the radius of its circular path? And that will wrap us up on circular motion. Hopefully this has given you a solid understanding of the behavior of objects that follow a circular path. If you found this video helpful, Hit the like button and don't forget to subscribe to stay on top of all the newest physics lessons. Thank you for being a part of the College Physics series. I look forward to seeing you in the next lesson.